All right, so we've already actually started a little bit, only like a couple of minutes. What we're drawing right now is the picture of the magnetic field of a bar magnet. And then I just got done discussing this idea over here on the right side, in which if there is absolutely no bar magnet there, the North Pole is not defined by the physical object, but defined by where the magnetic field is the strongest. So in this particular case, that would be the North Pole because the lines are leaving and they're the densest there, just like they're leaving and they're the densest here and going in. So that's the South Pole, and it's the densest there, so it's the South Pole. Obviously, my picture's not perfect. You could maybe argue that there's a denser spot, blah, 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 whatever. Okay, questions, concerns about that? Okay, let's show you another method of seeing this. I don't want to post it. Well, I can't show it right now because our internet's out anyway, but I'll try to find the video for it. There's a great video of what I'm about to show you, but the slow-mo guys did it in actual 3D space, which is really cool. But if you would just come up here, yeah, let's come up actually front real quick. I've done it on the desks before, but there's a slight slant to that. So come on up front real quick. Grab me a couple of those textbooks over there. Maybe whichever one. Okay. So real quickly to talk about why certain things were like off a little bit in the lab. Do magnets naturally store next to each other? No, they naturally flip and go the opposite way. As these magnetic fields are running into each other the opposite way, they're kind of slowly canceling each other out very slowly over time. Since, as we discussed yesterday, it kind of takes liquid metal to go quickly. These solid metal ones are not going to change as quick, but they are changing slowly over time. Every single year that I do this, they're a little bit worse. So luckily I have this. You remagnetize it. We'll talk about that. Sounds like a big acne product. So I'm going to place these here with for spacers. Putting magnetic in the middle of this, it's just so that it can all be one level. Now put on here a piece of paper. This is iron filing, so just pieces of metal that are completely neutral. But what do these metals do in a magnetic field? They go line. If I put a little bit, you're not going to see much. The more I put on here, see the magnetic field lines coming out.
Whoa. That's better than my drawing, I would say.
Okay, and if you did have your course compass, in this case, this is the north, so it should be leaving. I've done this correctly, but yeah, there you go. So you can see that the lines match directly where the compass is going, and so weirdly the lines are back this way to wrap around over here. There you go. Also, the other reason I did that is to show you, because we're not going to do the same picture. So that is a bar magnet. You'll notice that the bar magnet has a very similar look to a single positive and a single negative in terms of electric field. Very similar, not quite the same. But if I use a horseshoe magnet in its place, a horseshoe magnet that is, yeah, I mean, a horseshoe magnet is probably actually what you see most often in the cartoons. Horseshoe magnet looks, that is similar to our, as best as we can do, our uniform electric field. But yeah, you can see the lines go straight across in this particular case.
How do you know which side
It
is
looks
north
like
and south?
it does right now.
What?
Well, ultimately, the correct answer is whichever way the field's pointing. So, but I don't know this is perfect either. So, in this case, it's pointing towards south. So that would be south. It should be. Yep. There's north.
Oh,
There's south. And that should be correct due to the fact that I just recharged it just a second ago. All right, go ahead and have a seat.
No, side pieces is looking like fruits.
Like I said, if you haven't seen it already, I'll try to remember to post it when the internet comes back on. But here's the great thing, by the way, about cleaning up magnetic filings on the desk.
But then you get it all over the board. You have to like pull them off.
Yeah,
You could definitely turn off your phone with a weak magnet.
Do they hurt?
Violence.
You could probably get stuck in my finger and guarantee it.
Sorry.
I would probably do that.
You mean what? Get stuff in your finger?
Yeah, knowing me, it would probably get stuck in my finger. Let's be real.
good. So, to show you the bar magnet up here,
I know what you're doing. Okay.
the bar magnet should look like this. Well, that's just a terrible U. Oh, back to the. Yeah. So it's as close as we can do to a uniform electric field. There you go.
Do they not go around the bottom at all?
They do. We don't usually worry about it because that's not kind of where we're at. Now, the thing is, what's that?
Is the whole thing magnetic? Like,
Yes, absolutely.
it's just
Now, I think I mentioned this yesterday. We'll say it again. The Earth. So, Canada, okay, South America, Europe, Africa. Nailed it. All right. The Earth. Oops, that's right. Acts like a bar magnet. This side being south, this side being north. Right? So, when you draw over top of that, you see certain things that we were discussing yesterday. So which way does a compass point?
south, north-ish, south.
So just say, when you're saying that, because you're both right, right? So what you want to say when I'm asking that is you could either say north geographically or towards the south magnetic pole, which are the same thing, right? South magnetic pole, as we discussed yesterday, is in northern Canada, and the northern pole is in Antarctica. But the main thing also to know on that is they're not directly on the poles themselves. So if you're here, right, you're here in America, you're here in Illinois, what are you really feeling? You're actually lining up with one of these lines that are crossing. And so what should it mostly do? Well, you can see right along here that for the most part, magnetic field lines practically parallel to Earth's surface pointing towards north. And if you hadn't thought about this before, it's actually a good thing that they wrap around because the Earth is curved. And so to stay actually in line with that curve, they kind of need to curve around. Yeah.
So how do compasses work in different countries?
So for the most part, they go north. The globe that I showed you the other day is not perfect. I can't tell you whether or not they fully knew this because I am ignorant. They don't know about it. But you can see here that in Europe, compasses just point northwest, right? Now, I don't know if they knew that at the time. I would guess yes, because a lot of times they're vastly more intelligent than we give them credit for, and a lot of our knowledge comes from just like basic elementary, like literally being in elementary school, it's like compasses point north, compasses point north, compasses point north, and maybe they knew different. Or maybe they used that in addition to other methods to make sure they were on track, looking at the stars and stuff like that. But yeah, essentially they point northwest. it would still guide you towards the general direction specifically of where you're going, even if you thought it pointed north. So, questions, concerns about that so far? All right, so let's get into it. So right now, what we have is we have what three metals make magnets? Iron, cobalt, and nickel. If you ever forget, they're right in a row, 26, 27, and 28, right up there, Eco 9. Okay? Iron, cobalt, and nickel, right there in a row, probably for a reason. Anyway, which we'll get to a little bit later.
Oh,
Why is IPS doing electricity?
Oh, is it IPS?
All right. So this is what we were just showing you a second ago. This is the magnets of north and south, like you saw a second ago. Or you can do the the opposites right next to each other. This is practically completely identical to the positive and negative picture that we did before. And then, of course, this is the opposites, and this is very similar to the electric field when they were the exact same going next to each other in that particular case. And this is what I was talking about just a second ago. Here's your picture of Earth. You'll see the south magnetic pole is in the north geographic, although it's not quite perfect. There's the that means there's the magnetic axis and there's the axis of rotation. Earth's magnetic field, here you go. You get the general gist right here. Even in America, things don't directly point north. I mean, this too might be a little bit more violent as far as kind of like whether how far spread out they are. But you can see over here in Montana, they do not point north. They actually point northeast in that particular case.
what makes the magnetic field on it?
We haven't got to that yet.
Oh,
We haven't got to
there's
that
like
yet.
no iron. So.
What's that?
There's no iron, so I didn't know.
You sure?
In the middle of the earth?
Oh yeah.
There's
A
a
lot?
lot of
Yeah.
Really?
There's so much
Yeah.
iron.
And it's really
Okay,
hot.
it's-
It's primarily what it is. What's up?
So if you like had a compass in like Montana, would it be pointing like if you had it like holding straight, it would be pointing like
Northeast.
north? So how do I
Yeah.
Yeah. So how do you?
You either rectify that or you don't care. What does north really serve? You don't need to know where north is. What you need to know is just your relative bearings, right? You need a general sense. If you used everything as north and went east, right, to find a place, would it get you pretty close to what it is you're looking for that is east, even if it wasn't perfectly east? Yes, it would get you out in the right area. So, they have found magnetic bacteria that use magnetic fields in order to kind of align the way they need to. They are pretty sure that birds are able to fly south because of their actually feeling of magnetism within them as well. Also, the numbers that you see printed on airports are actually magnetic field lines. Why does that make sense as opposed to? Yeah, because the compass that is being used in the thing will tell them what magnetic thing to line up with, because that will actually tell them more so than the other, because they don't know. If you get, I believe, on the Apple phone, if you have an Apple phone, you have a compass app on there. Does anybody have an Apple phone and know there's a compass app on there?
Yeah.
Okay, there's a setting on there that says point north or point true north. What's that? I can't remember where it is.
Wait, which one do you call true north?
Where is it?
According to like look on
Oh, I don't think I have it.
North would be north.
The compass.
It's in like the
This
little
does not-
utility.
Wait, yeah, you have to go on my
settings.
settings.
Yeah, where is it?
Mr.
Did you find it?
Yeah.
Okay, what does it say technically?
It just says use true north compass.
Yes. So
Wait,
it probably is default to true north, right?
No.
Oh, it's default to north. Okay.
Wait,
So true north is actually then, I can't remember exactly, I couldn't remember which order it's in. True north is actually the south magnetic pole that it's having you point to. Now, does your phone actually have a compass in it? Does it actually have a magnet in it? No, that would be very, very bad. Well, that's not entirely true. It does have some magnets in it, but very importantly, you can't just put like a big enough magnet in order to figure that out. So yours is entirely programmed based on GPS and figured that it does calculations and whatnot. Yes.
I don't these match.
Well, I told you before, a regular compass is not going to work inside of a building for reasons that we have not yet discussed. All right, let's keep going. All right, so what we have now,
Oh my god, equations. Let's go.
we got equations.
Use.
All right,
Let's go.
what we have now is this. Here's where we're at. We know 3 materials can become magnets. What are they?
Iron.
Cobalt, and nickel. We know currently that magnetic field lines come from what?
The north.
Permanent magnets. Yes. The north end of a permanent magnet toward the south end of a permanent magnet. Now, to discuss where magnets come from or why, that's the next thing. Well, that's the second to next thing. Right now, what we're going to discuss is what do we define magnetic field as? To get into that, let's remind ourselves very quickly of what I said at the beginning of this. What other field do we already have? We have electric field. So let's remind ourselves of electric field, what it is, what it does, because it matters here. Here is my electric field. I'm drawing it in red, specifically drawing it in red. I'm saying it out loud so I remember, not you. All right, what does an electric field do?
It points towards what way a positive would
Close. Not which way it would go.
Towards like positive.
It points towards the direction of force on a positive.
Yeah.
Now that's not inherently the same thing. You're making the assumption that it's starting from rest, blah, blah, blah. Okay. Now, we already learned which way magnetic field goes. It goes from the north end of the magnet to the south end of the magnet. Or in this room, then, ideally, which way is magnetic field? If we were not inside, which way should our compasses point? That way. Because actually, really nicely, I don't know if you guys saw this or not, it works out really well for us where we're at, that being in Illinois, it mostly points straight north. It's not perfect, but it's pretty darn close to straight north. So, hooray! All right. So now, what's the deal with freaking magnetic field? Okay. Magnetic field uses the letter B. Why? I don't know. I'm sure it's some Latin thing. Look, it was magnetic field. I don't know, in some other language. Who knows? Okay? But it's B. Also, M has been heavily in use since the beginning of physics, so let's not use another thing with M. But B is magnetic field. So electric field is if force goes this way. Sorry, if electric field is this way, you put a charge in, there's going to be a force that way. Magnetic field requires basically how many different? It requires a couple different things in order to get a force. Number one, magnetic field also puts a force on charge. Magnetic field will also put a force on charge. But the weird thing about it is that charge has to be moving. Okay? If charge is not moving, you're asking why? Okay, why does gravity? This is why I'm saying magnetism is weird. There's certain things I'm just going to have to say, why are they the way they are? We measured it. Sorry. Okay? It's weird. Get used to it. So, in other words, if the charge is moving also, sadly, I got to do 3D on you. Okay? So I got to talk about how to draw 3D vectors real quick. It's not that hard. But if I want to go into the board, a vector is an X, okay? If I go out of the board, the vector is a dot, okay? This is like thinking, think about an arrow. This is like the tip of an arrow, and this is like the feather of an arrow. It's the best way to think about it. So, if my velocity of the board, if my velocity of a positive charge is going in, let me use another color. If the velocity is going into the page, this is where we use our right-hand rule. Okay? Right-hand rule. Your finger, I told you the joke before, but it's really easy, and you'll kind of understand it a little bit more now. The finger's like the gun, pew pew, that's your velocity right there. So in this particular example, right, you take your magnetic field, you point it into the page. Okay? Now, force is great. Yay, force. Thumbs up for force. Okay? And this is magnetism because F magnetism. Your easiest way to do this is actually to match velocity first and then just rotate your hand. So this would mean, which way is the force on this charge? Down.
Ew.
Oh, right.
Just watch your field.
Wait, so what is your index?
What's that?
Yeah, wait, can you show again?
Yes.
This
Velocity, pew pew.
Pew, pew, pew.
Pew pew, shoot the
Yay,
gun.
force.
Yay, force. F, magnetism.
Okay.
Okay, so
So what
in honor of Brianna, even though you kind of know where this is going, you are all the sun, and I am the earth in this particular example. Okay, here I'll go with the Illinois. Okay, you regularly shoot alpha particles at me, which we'll find out in a couple chapters are positive particles. So go ahead, shoot alpha particles at me. Thank you, everyone. Everyone do it. Come on, here we go. All right, cool. Which way does Earth's magnetic field point? Which way does Earth's magnetic field point? Go ahead. Points north. So use the right hand rule. Come on, let's do it. You're using left hand. You can't use left hand. We'll talk about that in a second.
Strange.
Yeah, it's mirrored. Yeah. So which way do charges then go? Which way charges push then?
They're right.
They're pushed. Yes, they're pushed west. Sorry, east. They're pushed east.
Wait.
Okay. And through this particular process, we'll talk a little bit more why later on. But that magnetic field sort of acts as a barrier that takes charge and does not let it get to Earth. A lot of those alpha particles, some of them do, but not a lot of them get to Earth, and so they come in and they go around. Except, here's the deal. Velocity and magnetic field must be perpendicular. So stop looking at that. It's fine. Even if it falls, it's okay. Okay. Magnetic field and velocity must be kept perpendicular to each other. There are three things necessary for it to get a force. One, there's got to be charge. Two, there has to be velocity. And three, magnetic field must be perpendicular to velocity. So then the question you ask is, what happens if magnetic field is not perpendicular to velocity? And the answer is there's no force whatsoever. So, is there a location on Earth where, say, the velocity coming in would go parallel to the magnetic field? At the poles. Right here at the North Pole, which way does magnetic field go? Down into the Earth. And so if charge comes along parallel to this, does it have any force put on it? So that charge definitely hits, right?
Yeah.
And where is the location of the Aurora Borealis?
Why not? Why is it anyone?
Thus the reason of the Aurora Borealis. There is a south, yes, there are south lights as well.
Why don't we hear about those? Because there's less people down there.
You can look it up. There's south lights as well. How many people are in Antarctica to see them?
Aurora Borealis.
Yeah, Aurora Borealis there's the northern one and there is the southern one as well. Yeah, as lights come in parallel. Yeah. So let's talk the math real quick. Then there's of course the question of what if it's somewhere in between, which we'll get to in just a second. So here we go. Come on, let's do it. Here we go. All right. So magnetic field, I wish they would start with this. I don't like that they start with that equation right there. But here, magnetic field is defined as the ratio of how much force per charge and velocity. And we'll talk about this sine theta in just a second. But to start off with, let's assume you want to ask the question, what angle is that? That's the angle between magnetic field and velocity. So if they're perfectly perpendicular, that means that angle's 90. And what's the sine of 90? Try again. Sine of 90 is 1, and thus at 90 degrees, the equation for this is force over QV, otherwise known as Tesla. Tesla is the measurement of magnetic field. That also has the units, which we'll talk a little bit more about later, so write it down now. That's Weber per meter squared. I don't know if that will matter this chapter as much as it will next one. So this is the definition of magnetic field. It's the ratio of force to charge and velocity. And it's weird to have like three variables moving around here, but basically here's what it says. If I get more charge, I'm going to get more force, right? Because this ratio is staying the same. If I get more velocity, I'm going to get more force. And you can see that by rearranging it back into this equation right here at the top. More charge, more velocity will ultimately give me more force. Does that make sense? Okay. Now the direction of that, the way you figure out the direction of that is the right-hand rule. But what if they're not perfectly the same? That's this angle right here. This angle is between velocity and magnetic field. So for example, if the velocity and magnetic field were like this, okay, so instead of 90 degrees, I move it, okay, now it's at 45 degrees. What does that say? Well, my finger, I can't exactly shrink it right now because I'm not very good at that, but my thumb should be about 71% of what it normally is. Where did I get 71 from? What's that? Sine of 45. Sine of 45 is just 0.71, right? That's what percentage is in that particular axis. So units on this, just to show you real quick, Tesla, a Weber, they're going to be, just like you can see right here, newtons, coulombs. That should not say meters per second squared. That should just be meters per second. Or should it? Hold on, let me check to make sure. Well, force is already up there though. Force is already in newtons, yeah. Yeah. Yes, I know 100% it shouldn't be there. That squared should not be there, so when you write it down, don't write it there. Because here's another thing to point out, okay? Instead of talking about coulombs times meters per second, it's very unlikely that we're going to be able to move charge, and I'm going to be able to take like an electron and throw it across the room, right? We're not going to be able to see that really well. What will be a decent way of moving electricity across, or charge across the room? What did we talk about in the previous chapters? Current. Current is the movement of positive charge from one place to the other. And if you look, again, get rid of that squared. Instead of coulombs times meters per second, let's rearrange this. And meters times coulombs per second. What is a coulomb per second? Ampere. It should not be a square. There's no square there. Should no square there. Okay. Because Teslas are very, very small, we have another unit to kind of measure small amounts of it. So like, to give you an idea, the magnetic field of Earth, I want to say, I always look this up. I have to look up everything. I think it's like 3.2 microtesla. Okay, so microtesla is a very normal scale for Tesla. But because of that, we're going to make it bigger by saying 1 Tesla is equal times 10 to the 4th Gauss. So we can write like a much more normal number of Gauss in that particular case. Gauss.
I've heard that guy's name before.
If you've heard of a Gauss cannon, I can't remember. Maybe I'm saying it wrong, but yeah, Gauss. Okay. All right. And what you're looking at right here is the exact same equation as the top. When are you going to get force maximum out of magnetism? When the angle is 90, when they are running perpendicular to each other. So again, what really messed me up when I was first doing this, in case it's hitting any of you right now, is that, wait, how could, there's like 3 different possible angles between force and this and force and this and these two. The angle is specifically between these two. The thumb, if you think about it like a plane, let's say magnetic field is pointing this way, okay? And the velocity could be anywhere along here. Those can change their angle a ton. But if that's the case, if magnetic field is that way and velocity is that way, then the force is definitely into the page, okay? If you look at this entire thing, doesn't matter where you put, actually, it doesn't matter where you put velocity and magnetism on this plane, the force is either going to be directly out of the page or directly into the page. Okay, sorry, out of the page or into the page. Does that make sense? Now, one thing that's kind of confusing, when you're looking at a screen, I should have done it up here for the people that are here.
This really sucks for the video people.
Yeah, agreed. Okay. So, speaking of the sucky thing for video people and making sure that when you're doing your homework, this doesn't mess you up. When you're looking at a page on your homework, north, south, east, and west can be a little bit confusing because if you try to spatially do this, which way is up?
Technically,
No, if I say up, I mean up.
Out of the page.
Out of the page, correct. So, what I would suggest when you're doing your problems, luckily most of you are going to put paper down on the things. make sure that when you're trying to do it, write it, transcribe it onto your page so that you can correctly in this space, even if you don't match perfectly north, you have north, south, east, west in its appropriate plane, right? So up can be up and down can be down, and out of the page, into the page. Yeah, I know. See what I mean here? So like technically up is actually like if I turn it like this,
Hold on.
up on this is actually north in the space, which is going to be super messy in your brain. So again, don't try to solve these necessarily when you're looking at a screen. Transcribe it to a piece of paper so up can be up and north can be north. Let's just do this real quick. I have a velocity going south and magnetic field is down. Which way is force?
Wait, what?
I have a velocity going south, magnetic field is down. Which way is force?
Velocity, force is
Down is down.
That way.
That way. That
Yes.
way.
So south, I point south,
Oh, wait,
I point south, okay, and magnetic field is down, so force should be
That way.
east.
East.
East people. Yeah.
Wait. I thought you had.
What's that?
Wait, never mind.
It's east. I got you on this.
So,
Okay,
could you rotate things to make it worse?
100%.
Yeah, okay.
Yeah. Why? This is complicated as it is. Could I make it worse? 110% I could. Okay. Now, what changes? What changes if magnetic field is up? Well, this is the one kind of you did earlier, right? There we are. My force now goes west. My favorite part of teaching you this particular trick is I love watching you guys during this particular test. You see someone like, especially like, I would highly suggest a lab table because I see students sitting in a desk going like, is it this way? All right, I got the answer. Someone write it down for me. I can't reach my pencil. All right, let's move on.
Is this for positives or?
Excellent question. Okay, so the right-hand rule exists for positives, okay, with the caveat that negatives do the opposite. Now, what you could do, I don't suggest this based on past experience with students, and this stuff is complicated as enough. What you technically could do is your left hand is a mirrored version of your right hand. So if you match them, look here carefully, velocity pointing the same way, if I get the magnetic fields pointing the same way, the forces go opposite direction. So technically, if you will, negatives follow the left hand rule, which I put in air quotes and cannot suggest this enough. Don't do it, okay? You will mess yourself up 10 times over what you would. Use the right hand rule, see negative, and know that it goes the opposite way. What I'm doing, if it's me, if it says an electron is traveling south and the magnetic field is down, I'm using right hand rule, I'm pointing south, magnetic field is down, so I see that force would be east for a positive, and so it is west for an electron. Questions, concerns there?
So you just flip.
Forehand rule.
You just flip the force. And again, you can see that if you were to use like the left hand in that case, but cannot tell you how many times I have seen students try to be like, I'm going to use the left hand rule, and then they're using the left hand rule when they're not supposed to in the right. Just use the right hand, get used to it physically, get used to using that hand. All right, moving on.
My hands are
I've been doing it wrong. What have you been doing?
Okay, so right now, again, I want to put a giant caveat on where we've gone so far, and I got one more thing to hit today, and I want to stop because I want you to go work with this in your homework and get kind of a little bit more used to it before we worry about what's next. What we have right now is we know that magnets come from 3 metals. How do we know this? Experimentation. I showed you the other day, putting a magnet next to aluminum. You can try this kind of messing around with my magnets when you're free. You can check to see whether or not stuff in the room is made of iron, cobalt, or nickel. Like, does it attract? And if it's next to aluminum or something else, or nickel, or any other thing, it does not. Now, most things I will tell you, most metals will attract because humans make most of their stuff by some iron alloy. Even steel is not a different metal, it's an iron combined with something else. So, we found that all magnets are one of those 3. We found that norths repel, opposites attract. Norths and souths repel, opposites attract. Experimentation. Okay, we found the direction of magnetic field along a bar magnet and around a horseshoe. Thank you very much. Okay, we found that basically all magnetic fields come from these permanent magnets as of right now. Okay, and right now what we are working on is what charge does in a magnetic field. Right? Okay, so I got bad news for you. Here's the problem. What did I just say earlier about the direction of force relative to velocity? It's going to be 90 degrees. And what does force cause?
Acceleration.
And what happens when acceleration is perpendicular?
Spin.
No.
Circles.
No.
Centripetal acceleration
No.
is back, baby. All right. It's not that hard, guys. Now, let's do some basic math with this. All right, here we have, you see in the picture, what's the direction of magnetic field according to this picture? When you don't have the frame of reference, you can't say down, so the best thing you should say here is into the page. Magnetic field is into the page. Again, I can't say, you do whatever you want, but I always, me personally, I always match up velocity first. Always match velocity first, and then just rotate around that particular axis. So if we look at this guy right over here, you can see that all of this does match, and you can try it out yourself, right? Magnetic velocity is up, magnetic field is into the page, so force goes like this. If magnetic field stays the same direction, then notice which way it's going to, oh crap, it's going to make circles. All right, so Newton's second law is what? Well, give me the whole thing, dummy.
Force equals mass times.
Net force equals mass times acceleration. I was looking for just a gentle reminder that in circular motion, forces towards the center are always considered positive. Now, the good news is, it's going to make this vastly easier, is how many forces are we probably going to have to deal with on this level? One, because electric field does not run perpendicular, it pushes it in the same direction. So, what is that force probably? Force of magnetism.
I thought it was B.
You can write FB as well. It's fine. Okay. Capital B is magnetic field. I will always do that. But if you want to write FM, force magnetism, that's fine too.
Okay.
All right. Now, M is what property of mass? There's two properties of mass. What are
Inertia.
they? Inertia and
The other one.
the other one.
Stuff.
Come on. Gravity. It is gravity. Correct. Why don't we deal with gravity on this level?
Because it's not
Too
like
small.
So ridiculously small it shouldn't affect things. So we don't have to worry about it. So that is the property of inertia. Cool. What is the equation for acceleration when it's run perpendicular to velocity?
It's alpha.
VT squared over R.
Correct.
Oh.
Nice.
Okay, and we just learned a second ago, what is force magnetism equal to?
What is it?
What did we just learn a second ago that force magnetism is equal to?
QVB sine theta.
Let's go ahead and assume that they're perpendicular, so I'm just going to say QVB. This math right here, if you can do this and follow this, will be probably 90% of the work, and then it will ask for various things. It'll ask, what's the velocity? Or it'll ask what the radius is. Or it'll ask what the ratio is of charge to mass. Actually, there's one more simplification we could make here, though.
Yeah, I was gonna say there's two velocities.
There's two velocities, correct. Now, the one on the right is squared, and velocity tangential is just saying that is the velocity tangent to the curve, and this is the straight up velocity, so are those the same amount? Yep.
Wait.
So that will cancel with one of those, leaving us with this. So, if you knew the charge and the mass, and here's the major thing, guys, remember, if I say proton or electron, what do you know about both of them? You know charge and mass, right? If I say a proton is traveling at so fast, well, then you know charge, you know mass, and you know velocity. And if I tell you the magnetic field, you could find the radius of the circle that it goes around. Okay? Or you could mix it up. I could tell you the radius that it goes around, and blah, blah, blah. You could figure out, actually, interestingly enough, I could make this happen. Watch this. There's a lot of stuff I could do with this that they're going to do on the next page. But let's do this. Let's go charge over mass, just by dividing that underneath, is equal to velocity over magnetic field times R. That's a mass spectrometer equation right there. Mass spectrometers are devices over in chemistry to figure out the ratio of charge to mass of a particular object. What do? They set the velocity of a particular material. I'll show you how a little bit later on. It's actually pretty easy to set its velocity. Okay. Then they set the magnetic field. Knowing this, all they need to then figure out is how far of a radius does this object go around when put in a magnetic field, and wherever they detect it hits, the radius directly decides what this ratio is, and that ratio tells them exactly what the material is made out of. All right. But this is why I just showed you this work on the last page. Here's the work that the slides just showed you. Boom. Now, where does that come from? Again, as we showed you on the last page, this is sum of forces equals mass times acceleration. That guy's acceleration, that guy's force magnetism, and then rearranging this, they canceled the V's and they got the radius. They solved for radius instead of this particular circle. But quite frankly, as I mentioned before, if you can do super basic Newton's second law and remember QVB and N and VT squared over R, it's kind of plug and chug a little bit beyond that point. Yeah.
Then from the sun to Earth, what would that circle look like?
So, okay, interesting thing along that particular front.
Or is it this line?
Number one, the velocity of alpha particles as they come in towards Earth, okay, would not be exposed to very much of a magnetic field, right? The magnetic field is created by Earth, so it gets weaker and weaker and weaker as it goes out. So what happens is the charge comes in, okay, I'm going to try to flip you off here. The charge comes in and it pushes east, so it goes in a circle. Now, if the magnetic field stayed the exact same strength, then it would just go in a circle forever, and that would not be good for us. There'd just be this whole like circular, like giant death circle up here. Okay? But the thing is, as the thing comes out, what happens to the magnetic field? It gets weaker. So as it gets weaker, you've got magnetic field this way. There's a force that way that is weaker than the force pushing that way. So what ends up happening is it kind of circles around till the backside and flies off. Also, in this particular picture, I'm not going to spend long on this because it's not particularly important, but what you're seeing right here is the helical path. Well, if you deal in three-dimensional space, okay, what you can kind of think of is forget the x-axis for a second. Okay, so here, in the sake of this picture, I'm going to say this is y, this is z, and this is x. Okay, this is x, right? So if magnetic field was along the x, okay, and I have a charge coming in here, see here that the force would be up, right? And as it goes around in a circle, it would just stay in that circle forever. But if it starts off with any amount of component in the x doesn't do jack squat as far as magnetism, so it's going to stay at a constant velocity in the x. So imagine this object's going in a circle, but it's at a constant velocity in the x. That's where you get this helical shape from in this particular setup. All right. So one thing that you'll see here is what would you expect a charged particle to do, assuming that nothing's on it outside of a magnetic field? Well, you'd expect it to go straight. So what you're seeing right here is exactly what you expect, Newton's first law, and then we have a magnetic field pointed out of the page. So we can see velocity here is up, magnetic field is out, so force is to the left, meaning it should turn to the left, and it stays, sorry, I'm doing this poorly here, magnetic field is out, so it should stay up and then go in a circle until it leaves the magnetic field again, and then it would just go straight again. Make sense? Cool beans. Now, as I mentioned before, a single charge like this is not going to be very easy for us humans to do. But what is easier for us to do is to create current. So, what we're going to do with current here is you'll notice I've got a battery. And I got this battery's got a switch. So we've got positive coming out of here. So current is the flow of positive charge. So the really nice thing about that is that basically you can use the right-hand rule again. Instead of velocity being here, what do you put here instead? Current, because it's the direction of flow of positive charge. So right down here, you'll notice a magnet, north, south. So which way is the magnetic field of that? Down, towards the south, away from the north. Yes? And you'll see here from the path that we're following, this is positive flow, this is positive flow, this is positive flow. So there would be a velocity pointing that way, a magnetic field pointing down. So what is the bar going to do? The bar is going to push in, and I will show you that demo tomorrow. Like straight up 100% we can do that in here and show you moving wires because of this. As a matter of fact, if wires move because of magnetism, sweet. If we scale up the wires and we scale up the current and we attach this to something, what have we just essentially, we did it already, but what did we invent?
Magnet.
Magnets cause motion. Motors. This is the invention of the electric motor. Motors have to run on magnets. Every single electric motor has a giant magnet inside of it to be able to use this principle right here. All right.
Well, that's why I named my electric motor with a magnet.
Did you do? Okay, so here we go. Now we have a magnetic field pointed into the page. You'll notice there is no current, and therefore the velocity would be 0. So should there be a force?
Correct.
Absolutely not. Just slow your roll.
So rude there.
Tone is like 90% of conversation here. All right, in this particular case, current is up. So current is up, magnetic field is in. See from the force that it should be pushed to the right, left, the other right. Okay, and in this case, current is down. So current's down, magnetic field is still in. So force is pushed to the right, the actual right. Now, good news, bad news. Good news is, and the bad news is, we don't really have to change the equation all that much. The original equation right here was this. Well, remind me real quick what velocity is. What is it broken out?
Meters per second.
Meters per second, or displacement over time, or distance over time. If I break that down out into instead, force is equal to charge times displacement over time times magnetic field. That's the same thing, right? What's that?
Current.
That's current. Now, they're going to do it a little bit more complicated than that, using something that we've already done. The volume of this space is going to be the area in here times the length. They're going to call this L. And the number of charge carriers would be where this tiny little n is charge density, or charge carriers per volume, times the volume would tell you the number of carriers, right? Numbers per volume times volume tells you the numbers. Everybody cool with that? If not, please let me know. So QVB times the number of charge carriers would tell us the total amount of force. So in other words, what they're breaking down a little bit differently is this. This is the force on a single charge. This is the equation for a force on a single charge. So to get the force on a wire, we're just taking the force of a single charge times all of those charges. But if you look at the math of that, it's been a minute, but we defined current as this right here. That came from a definition, it was a minute ago when we did it a few chapters ago. That is the charge density times the charge times drift velocity times area. So if all of these things, where did I just lose it? Hold on. NQ, V, VD, and A. N, A, Q and VD, if all of those combine together into I, you get exactly what I was going to show you a second ago. That force is equal to magnetic field times current, and instead of delta X, they used what variable? They used L, the length. So, force equals Bill. Or, if they are not directly lined up, same thing as velocity and magnetic field. If current and magnetic field are not directly lined up, like it shows in this picture, then we have the sine theta. What angle would this, what two vectors would this be between? Actually, they don't have.
Velocity and
Oh, not in this case. Current and magnetic field. So if I have a magnetic field and a wire running parallel to that magnetic field, will there be any force on it? Absolutely not. Absolutely not. So what you have right now, okay, by the way, this right here explains how speakers work. Okay? Every single speaker has a magnet inside of it. If you look at this picture right here, look what happens. All they do is they take a piece of wire and they wrap it around here. So what you're seeing here is this is technically these three dots in a row and these three X's in a row are all one wire. They're just kind of cutting it so you're looking at it right here. So if I run current kind of like into on the bottom and out of on the top, and I've got north in the middle and south on the outsides, what's going to happen when I put current this way? Well, when I put current out, you'll notice, okay, current goes out, magnetic field goes up, so the force goes in. And the opposite is true right down here. Here the velocity is down. Sorry, the velocity is not down. It's into the page. The magnetic field is down, so that also creates a force this way, causing the speaker to go that way.
I'm confused. Wait, do it again.
Okay, so we'll start with the top. Top, which way is current? Current is the purple one. Current's going out, so velocity is out. Which way is magnetic field? It's up. So which way is the force?
To the right. What? I keep getting it to the right. What am I doing?
Okay, you're using the wrong finger. Velocity is out at you. This, start with the pointer finger. Start with the pointer finger. Which way should the pointer finger be going here? Out of the page. Okay, which way is magnetic field? If you don't like turning it like this, you can turn it like this. Well, for starters, what's messing with you right now, and you can see my positioning in physical space here, is you're facing the opposite way. So literally turn yourself around. Sometimes that helps. Point that way. Velocity goes out at you, right? Okay, magnetic field is up, so turn it so that it's up, and your thumb should point to the left on this page. Right, now, on the bottom. The bottom might be easier if you're struggling with this. Which way is current on the bottom? Into the page, magnetic field is down. So both of these setups should be causing a force going that way. Now, what would I do? I want to get my bass thumping. Okay, I just caused the speaker to go this way, right? I want to push it back the opposite way. What simple thing do I need to do with the speaker to make the force push back the opposite way? Not the magnets. Flip the direction of current. If current goes back the opposite way, if I flip the direction of current on this thing, what happens to the magnetic field? Stays the same direction. What happens to force? Goes the other way. So now to create a frequency, okay? To create a frequency, like, I don't know, like we talked about, middle C is 256 times a second, okay? What do I do with the current? I make the current go up and down at 256 times a second. And what's the force going to do? Go back and forth, pushing the speaker, therefore pushing the air, 256 times a second. And all of us are going to hear middle C.
It's all coming together.
Huzzah.
Why is it all together?
Well, because physics is all together.
Oh no.
What's up, Trevor?
So in a wire, the thing is actually moving is the negatives, right? Like the electrons are the thing that
We'll wait on this tomorrow.
Okay.
So, no, you go ahead. I was waiting on this. Go ahead.
So the negatives are the things that are actually flowing through.
Yes.
So why does the wire go the direction a positive would go?
Oh, I mean, okay, don't do that, because as we talked about before, it's the exact opposite for negatives, right? If we're saying negatives are going left, it's positive going right, right? Well, here we go. I got you. So here we go. So let's say negatives are going left, which I told you not to do this, but let's use the left hand rule. Okay, so here's the negatives are going to your right, right? And for sake of simplicity, let's say magnetic field is going down. So that would put the force out at you, right? Now, negatives going left
Oh, it's the same. Okay.
are the same thing as positives going
I get
right. Magnetic field is down, force is still the exact same direction.
Yeah.
Yeah.
The velocity we flip.
So the force is flipped for negative, but also the velocity is flipped. If you flip both of them, you're going to get the exact same effect. Okay, so what we have right now is what causes magnetic field? Currently permanent magnets. What can become a permanent magnet?
Iron, cobalt, nickel.
Cobalt or nickel, right? We know the direction of magnetic field as it relates to bar magnets and horseshoe magnets. And the last thing that we covered here today is what a single charge does in a magnetic field, QVB in the right-hand rule. And what we just ended with is what current does in that. And basically it's the exact same thing, except it's not just one charge doing it, it's a bunch of charges doing it at the same time. We could still use the right-hand rule, and tomorrow we'll step it up a notch. So please, 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 please make sure to do some homework tonight, especially you, Jackson. All right.